Hello everyone, good time. I hope you are all fine. Today we are going to look at another example about shear strength of reinforced concrete members, and we are going to see how to understand the amount of shear demand on a beam, and then after that we are going to see if the section has enough strength for the calculated shear demand, and if it does not have enough strength, we are going to design the shear reinforcement for the cross section that we have over here. You can see the cross section, the geometry is given, and of course some information is not given about this cross section like AS, but the information that we need for finding the shear strength are all mentioned in this cross section. The other thing that we can see in the problem is the configuration and geometry of the beam. As you can see, we have a two-span beam. The left span is 16 feet, and as you can see, this is the left segment, and then the right span is 6 feet, and the loading is also shown. We have uniformly distributed dead and live load on this beam. The question is asking us for drawing the shear envelope based on the necessary load cases and then design the shear reinforcement, assuming number 3 double leg stirrups are to be used for this section. The amount of loading is given to us. We have 2 kg per foot as the dead load, and then the live load is 1.5 kg per foot. Properties of the material are also given over here. F prime C is 4,500 and Fy is 40,000 psi, and note that this is Fyt, which means this is the yield strength of the steel that we are going to use as the shear reinforcement. So the first step is to understand the amount of shear force demand or the amount of shear demand that we have on the bending, and for understanding that we need to draw the shear force envelope, and shear force envelope is different than shear diagram. When we want to draw shear diagram, we have to consider the beam or the member that we have, apply the load, and then once we analyze the beam or the member, we can understand the shear force distribution and shear diagram. Shear envelope is based on considering several cases, and once we analyze the member under those several cases of loading, we have to just consider the maximum values at each location or at different regions from all of those several cases, and once we just draw the maximum values of all of those several cases, we can obtain the shear envelope. The question that we might have is, what is the basis of considering different load cases? How should I understand the different load cases that I need to consider, and what is the basis of these load cases? As you remember from the structural analysis course, we talked about influence line analysis, and we basically said whenever we have live load and we want to see, for example, maximum moment over here or a maximum shear over here, we can use that concept of influence line analysis to see where should I put, for example, the live load on this beam to get the maximum moment over here. For example, I said, or when you had this course, we said, if I want to know the maximum moment at the middle of the beam over here, I have to draw the influence line, which meant considering a hinge over here, pull it up, and then this will be the influence line for bending moment at this point. And based on this influence line, if I want to get the maximum positive moment at this point, I have to apply the live load in this region like this. And then if I want to know the maximum bending moment over here, I have to apply the live load in this region. Right? This was the discussion that we learned about influence line analysis and how it is used for finding the maximum moment due to changing loads or live loads on structures. Over here, we have a beam like this, and from the example that we solved during the class or during the presentation file, this example, we saw that at the middle of the beam, we have 0 shear force. And since it is 0 here, just based on considering live load covering all the span or the whole span, I consider 2 other cases, live load only on the left span and only on the right span, to get the positive and negative shear at this point. If I want to talk about that based on influence line analysis, we can draw the influence line for this beam. We have a simply supported beam and shear line or shear force at point D looks like this. This is the influence line for this point. And as you can see, for getting maximum positive shear, I have to apply the load over here. And for getting the maximum negative shear, I have to apply the live load over here. And this is what we did for finding the load cases and finding the shear envelope, right? I'm going to follow the same procedure in this example over here. I know that there is going to be lower amount of shear over here because of the supports that I have. So I'm going to draw the influence line for shear at the middle of the beam over here, or 8 feet from left support. And then once I draw the influence line for this point, shear at this point, I can understand where should I apply the live load to get the maximum positive and negative shear, and based on that I can draw the shear diagram for different load cases. Of course, having positive or negative shear does not have any real physical meaning, but in terms of just finding the amount of shear demand on the beam, it is useful to follow the procedure that we had for influence line analysis. So the first step for finding the load cases that are necessary to develop the shear envelope is to draw the influence line for the middle point of this beam over here. Of course, you might ask, why are you considering this point? Why not other points? And I have to say this is based on experience. Once you look at the analysis results of multiple beams or several beams under gravity loads, you will see that the critical point is the point where we get the least amount of shear force. Or like for the case of simply supported beam that we solved as the previous example during the presentation file, middle of the beam was the region where we got the 0 shear force, but based on shear envelope, we could see that shear is not 0 over there. If we have live load in just left or right span, the shear load might be different in that specific region. So the critical regions are the regions where we might get 0 shear force. Over here, I have this point over here, and I'm going to consider the influence line for shear at this point over here. For that, based on the things that we learned from structural analysis, I know the shear influence line diagram, or based on Muller-Breslau's method, I have to consider a cut like this, and I have to make sure the slope is not different from left side to right side. The only thing that I'm going to change is just a unit deflection or deformation. For that, we can draw a diagram like this. And as you can see, this is the influence line for shear at the middle of the beam. As you can see, here we have positive region, and here we have positive region, and over here we have negative region. So based on this influence line diagram, if I want to get maximum positive shear at the middle of the beam over here, I have to apply the live load in these regions, right? And if I want to get the maximum negative shear in this region, I have to apply the live load just in this region where the influence line is negative. Right? So based on this influence line, as you can see, this is the influence line for shear at point B. And then based on this influence line, I'm going to consider 3 load cases. The first load case is having the live load only on the left span and the right span. The second case is having the live load only on the middle span. And the third load case is having live load on all of the spans to finally draw the shear envelope for this beam that we have over here. So the first case is just having the live load in these regions. And now I have to analyze this beam based on this loading. Dead load was given to us as 2 kb per foot. So I have to include the dead load factor, which was 1.2. And then the live load factor was equal to 1.6. And the amount of live load was equal to 1.5 kb per foot. Based on that loading, we have to find the reactions. It is completely based on structural analysis. You have learned it before. For finding these reactions, I have to say summation of moments about this point, for example, equal to 0. Based on that, I can find R2. Once I have R2, I can say summation of forces in vertical direction equal to 0. And based on that, I can find R1. And once we have R2 and R1, the reactions, we can simply draw the shear force diagram. Once you do that, you can see this is the shear force diagram of the beam when the loading is considered like this. Live load is only applied on the leftmost and rightmost spans. This is just one load case. The other load case that we had was based on having the live load on the middle span, like this. This is the second load case. And again, these load cases are developed based on the influence line diagram. At first, I draw the influence line diagram for point at B, or for the point that we have in the middle of the beam, or point B. And based on that, I'm going to consider different load cases or different cases of live load application on the beam. We considered live load only on this span and this span for having the maximum negative shear at point B. And now I'm considering the live load only on the middle span to get the maximum positive shear. And then the final load case is having the live load covering all the spans. So this is the first load case. The second load case was this one. The analysis procedure is exactly the same. We have to find the reactions. Summation of moments about 1 point equal to 0. We can get R2. Once we have R2, we can say summation of forces in vertical direction equal to 0, and then find R1. And once we have these 2 reactions, we can draw the shear force diagram for this beam. I'm not showing you those procedures because you already learned those. Those are just based on a structural analysis. But once you draw the shear force diagram, we can get this diagram over here. So far we have one diagram like this. This is for the first load case. Then we have another shear diagram for the second load case. And the third load case that we have is having both dead and live load covering all the spans. Of course, dead load is always covering all the spans because it is dead. It is not going to change during the life of the structure. But live load, it is live and it can change and move during the life of the structure. And that's why we can play with the spans that are under live load. Over here we have all the loads covering all the spans. We have to analyze the beam under this loading, and once we analyze it, this is the situation that we have as the shear force diagram. So this is the third load case. Now, for understanding the shear envelope, I have to consider the maximum values based on these 3 diagrams and connect them to find the shear envelope. So I have to draw all of these shear force diagrams in one diagram, and that is done over here. At first, we have the shear diagram for the first load case, then the second load case, then the third load case, and all of them are shown over here. And then I have to just pick the maximum points and connect them together to find the shear envelope. And once you do that, this red line will be our shear envelope for this beam under the given loading. right? This is how we draw the shear envelope. The same procedure we had in the example that I solved in the presentation file. The only difference for this example was having just a simply supported beam, and the 3 load cases was shown to you, and then we could combine or draw all the shear diagrams together and connect the maximum values to get the shear envelope. The same procedure I followed over here, and I could draw the shear envelope of the beam, as you can see over here, and this is the shear envelope for the beam that we had under uniformly distributed dead and live loads. So the first step of the problem, or the first question, is answered. We have the shear envelope, which now we understand and we know what is the amount of shear demand in each region of this beam. Now that we know the shear demand, we can compare it versus the shear strength of the section and see if the strength that we have has enough strength or not. If the section does not have enough strength, then we need to add stirrups or shear reinforcement to increase the shear strength of the section. As you can see, the values that we have based on shear diagram are these maximum and minimum values. But of course, based on the analysis procedure, we need to know some other points inside the diagram. And during the analysis and during the solution, I will talk about these points and I will show you how to find these important points inside the shear envelope. First, I need to compare the maximum values in this diagram versus the shear strength of the section that we had, or phi VC. As you remember, when we were talking about shear strength of the sections, we looked at this diagram and we said if the amount of shear demand is lower than half of phi VC, we don't need any stirrups. The section has enough strength to resist the load. If the shear demand, or VU, is between half of phi VC and phi VC, we need to provide minimum shear reinforcement. And if it is greater than phi VC, we need to design stirrups and add them to the section. In this example, I have to first find phi VC and then see what is the comparison between these values and phi VC and phi VC over 2 to see which is the region that we have in our problem based on this diagram. So let's calculate the shear strength of the section, which means we have to calculate phi VC of this section that we have over here. We said based on the code, we have different equations for calculation of phi VC. As you can see, these are the equations. We said if we have AV, or shear reinforcement, smaller than the minimum amount of shear reinforcement, you have to use this equation. And in the example that we solved and had during the presentation files, we said when we are designing sections, we have no shear reinforcement or stirrups at first, so we have to use this equation. But the thing that is important in this equation are the parameters, which one of them is rho W, the amount of flexural reinforcement that we have in the section. That is one parameter that we need to use in this equation to find the shear strength. In the problem that we have over here, you can see there is no information about AS, the area of flexural reinforcement. All I have is the geometry of the cross-section and properties of the material. So based on these equations that I have, the only equation that I can use based on the information that are available in the problem is this equation. Of course, if we had and we know the amount of flexural reinforcement, we would use this equation, and based on the comparison that I showed you in the example that I solved during the presentation file, you saw that the difference between these two equations is not much, just a few pounds, and that is the difference that we have between these equations, at least for regular rectangular sections. So based on the information that are available in this problem, I'm going to use this equation to see what is the shear strength of the section. Now, let's see what is the shear strength or VC of the cross section without any shear reinforcement or stirrups. So VC is equal to 2 square root of F prime C plus the influence of axial load or NU over 6 AG multiplied by BWD. We have a beam over here. Beams usually don't carry axial load. In the problem, there is no information about axial load, so this is equal to 0. And to just give you the heads up about this part of the equation, I have to say it plays an important role when we are finding the shear strength of columns. Columns carry axial load, and that's why this term will be important when we are analyzing and designing columns. So over here, we have no information about axial load. It is a beam. This part is equal to 0, and the equation will be just 2 square root of F prime C BWD. So 2 square root of F prime C is 2 square root of 4,500. BWD is 12 inches, and D is 21.5. As you can see, B is 12 inches, and D is equal to 21.5 or 21.5 inches. Putting these parameters inside the equation, we can see VC is equal to 34.6 cubes. Based on the diagram that I had, or that we had over here, I have to calculate 5VC and 5VC over 2 and see if the amount of shear demand that I have in the shear envelope is lower than 5VC over 2 or between these values or greater than these values. So I have to calculate 5VC. Phi is equal to 0.75 for shear strength. Including that, we can see 5VC is equal to 26 kips. 5VC over 2 is equal to 13, about 13 kips, 12.97 kips. And these are the rules that we had for this diagram. I just summarized them over here. If the amount of shear load that we have in the shear envelope, or VU, is smaller than 5VC over 2 in any region in this diagram, we don't need any stirrups. If in any region in this diagram, VU, or the amount of shear, is between 5VC over 2 and 5VC, we need minimum stirrups. And then if the amount of shear in this diagram is greater than 5VC, we need to provide stirrups and design shear reinforcement in those regions. So I'm going to begin from point A. So this is point A, this is point B, this is point C, and this is point D. And these are based on this diagram. As you can see, I call this point point A, this point point B, this point C, and this point D. So I'm going to begin or start from left support and move to right and see what are the regions that we have in this beam, C and D. I have to find the regions where the amount of shear is equal to 5VC over 2 and 5VC to see in which regions I don't need any stirrups, in which regions I need to provide minimum stirrups, and in which regions I have to design the shear reinforcement. So this is point A. And now I need to see the location of the shear when it is equal to 5VC over 2 or 12.97. I know based on similar triangles, we can consider this triangle, right? And then in this triangle, we can find the location where the amount of shear is equal to 5VC over 2 or 12.97 kips. I know at some point the shear is equal to this value because it is changing from 33.4 to 2.1, but I don't know the location. So based on similar triangles, I can say I have one triangle over here. That is one triangle. And another triangle is the larger triangle, which is this triangle over here. So one triangle is this large one and another one is this a smaller one. For these two triangles, we can say, or we can write the ratios for the sides. Like for example, this side, which is 12.97 minus 2.1, divided by this side, which I don't know the value, but I know this point from this point, or the total length is equal to 8 feet. See, from this point to this point, it is 8 feet. So this side will be 8 feet. I'm going to multiply it by 12 to find the value in inches. 8 multiplied by 12 minus this value. I'm looking for this side or this length, and that is 8 multiplied by 12 minus this value, which I'm going to call x. That is one ratio, and the other ratio is for larger triangle, which is this side, which is 33.4 minus 2.1. That is this side, over this total length, or the bottom side of the triangle, which is 8 feet, or multiplied by 12 to get the value in inches. And then this should be equal to this ratio, right? So those ratios are shown over here. This is how I could understand and write the equation for ratios. Finding the location of 5VC over 2, or this point. And then I said we have two similar triangles. One of them is this one. One of them is this small triangle over here. And for this triangle, I can say this side, which is 12.97 minus 2.1, divided by this length. And if I call this, because I don't know this yet, this is x. So this length is equal to this total length, which is 8 feet. As you can see, 8 feet is equal to 96 inches. So this side will be 8 feet minus x, or 96 inches minus x. And then I have to write the ratios for the larger triangle, or this triangle, and that is this side, which is 33.4 minus 2.1. That is shown over here, over this side, which is the total length, this total length, which is 96 inches or 8 feet. So based on similar triangles, I can write these ratios, and by solving these ratios or this equation that I have, I can find x, or the location of the point where the amount of shear is equal to 5VC over 2, or 12.97 kips. If I solve this equation, the value of x is equal to 62.66 inches. And as you can see, this value is shown over here. So based on the similar triangles, I could find the location where the amount of shear is equal to 5VC over 2. Of course, right now I'm just looking at this portion of the beam, or A, B. After that, I have to move to BC, and then after that, I have to move to CD. But right now, we are focusing on AB portion of the beam, and in that portion, or in this region, we could see, or we could find the location of the point where the shear load is equal to 5VC over 2. So it means in this region where the amount of shear load is smaller than 5VC over 2, we don't need any stirrups. Now I have to find the location where the amount of shear is equal to 5VC, because we know in the region where the shear is between 5VC over 2 and 5VC, we need to provide the minimum shear reinforcement, right? So I need to find the location where the amount of shear is equal to 25.95, or it is equal to 5VC. The idea is the same. I have to use similar triangle rules. The only thing that is different is the triangles that I'm going to use for this part. For this part, I'm going to consider this triangle versus the large triangle that I talked about earlier. For this triangle, I know this side is equal to 25.95 minus 2.1. As you can see, that is shown over here. I have to say this side divided by this side. I don't know the location of this, so I'm going to call this region X, and then this region will be 96 minus X. So for this triangle, I can say this side over this side, or 25.95 minus 2.1 divided by 96 minus X is equal to these ratios when considering the large triangle, or 33.4 minus 2.1 divided by the bottom side, or 96 inches. That is shown over here. By solving this equation, we can find X, or the location of the point where shear is equal to 5 VC, and that is 22.65 inches. So in this region to this region, we have to provide minimum shear reinforcement. And then I have to see the amount of shear load at D inches from the support. As you remember, we said from the code, we need to consider maximum shear. As you can see in this slide and in this discussion that we had, code is suggesting us to use the shear load at D inches, or D distance from face of the support, because in the regions before this, the shear or the loading moves to the support and it does not really impact the beam. So we have to look at D inches from face of the support to see the shear load over there. In the example that I have over here, the shear we found as 5 VC was at 22.65 inches from the support, and it is almost D. If I look at the cross section, you can see D is equal to 21.5, and the shear that we found as 5 VC was 22.65. So it is just about 1 inch difference, and we can say we are approximately there. So based on these close values, I can say I don't need to find the shear at D inches from the support, because that will be some point very close to this value. And that means we can say in all of these regions that we have, which are almost D inches from face of the support, we can just extend the reinforcement that we have in these regions to the support. And this is how it is always done. I have to see what is the shear at D inches from the support, and then compare that versus 5 VC to see if it is greater than 5 VC or not. And if it is greater than that, I have to design shear reinforcement for that shear value. In this case, I could see D inches from the support was very close to this point, because it was 22.61 inches and D was 21 point something, 21.5. So we can say just D inches from the support is the same value, and that's why the minimum shear reinforcement that we are going to design for this region will be extended to the support. So far, we could understand the situation about AB portion of the beam, and I have to say in this region I don't need any stirrups, and in these regions I have to provide minimum shear reinforcement, right? Those are the information that I mentioned over here. For finding the minimum shear reinforcement, we know based on this diagram that summarized all the values, we are talking about this region, and in this region, this is the spacing that I have to consider between the stirrups, or in other terms, these conditions will give me minimum shear reinforcement. The spacing between stirrups should be minimum of these values. So the maximum spacing, and it is called maximum spacing because we are providing minimum stirrups, because the shear is between 5 VC over 2 and 5 VC. we are talking about this region. And in this region, we have to provide minimum stirrups. For minimum stirrups, we have to just give maximum spacing between the stirrups. And that maximum spacing is calculated based on this equation that we used before in the example and in the presentation. I have to just put the parameters inside this term or inside this equation and find the values. D over 2 is this much. 24 is just a solid value. AV, we are using double leg number 3 stirrups. These are number 3, and area of each leg is just 0.11 inches squared. That is area of number 3 bars. So 2 multiplied by 0.11 and then multiplied by Fy divided by 50 by BW. And then the other equation that we have AVFYT, the area of shear reinforcement, yield strength of shear reinforcement, and then we have 0.75 square root of F prime CBW. Calculating these values, you can see the result of these ratios, and then minimum of these values is equal to 10.75, right? So the maximum spacing that we can have between these stirrups is equal to 10 3/4 of an inch. As I told you earlier, just in this situation, the shear load that we have at the inches from the support is almost this value, very close, a bit greater. Just I have to move just 1 inch, but that 1 inch is a very small value, so I'm going to take this value as that value, and that means from point A to X is equal to 62.66, but this is not a value to be measured by tape measure, so I'm going to extend it a bit from point A to point X equal to 62 3/4 of an inch. Some value very close to this value, just a value that can be measured, 62. Just a value that can be measured by tape measure. From point A to this value, we have to provide minimum shear reinforcement, which means number 3 stirrups at 10.75 of an inch as the spacing. This is the spacing between the stirrups from this point to this point. And then from this point to this point, we don't need any stirrups. Those are the results of shear reinforcement design for portion AB or AB portion of the beam or this portion of the beam. Now I'm going to follow the same procedure for this portion of the beam or BC. And then after that I will move to CD. But right now we are looking at BC, and the procedure is exactly the same. At first I have to find the locations where the amount of shear is equal to phi VC over 2 and phi VC. As you can see, phi VC was equal to 25.95 and phi VC over 2 was equal to 12.97 kips. And based on similar triangle rules, I can find the location of this point, and also I can find the location of this point, right? For finding this location, I can say this is a small triangle. So these are the triangles that I'm going to consider. So I have to consider this a small triangle versus the big triangle that we have. And based on this, I can find the location of this triangle. We can say this side, excuse me. We can say this side, which is 12.97 minus 10.2 over this small side, which I don't know. I'm going to call this X, is equal to the same sides or the same ratios for the bigger triangle. This is the bigger triangle. This side will be equal to 43.8 minus 10.2 over this total length, which is 8 foot or 96 inches. Those are shown, as you can see, in BC over here. This is for the bigger triangle and this is for the smaller triangle, and based on this we can find the value of X, and that is 7.91. So phi VC over 2 is located at 7.91 inches in this shear diagram. Or in other terms, at 7.91 inches from point B, the amount of shear load is equal to 5 VC over 2, right? Now, based on similar equations, I can find the location of having VU equal to 5 VC. The triangles that I need to consider right now are these. The first one is this one. And for this one, I can say this side, which is equal to 25.95 minus 10.2 over this side, which I'm going to consider as X because I want to find the location. This is one triangle, and the other triangle is the bigger one. And for bigger one, I'm talking about this triangle. For this one, we can say this side, which is 43.8 minus 10.2 divided by 96. And that is shown over here. Based on this, I can find the location where the amount of shear is equal to 5 VC, and that is located at 45 inches from point B. As you can see, that is the 45. And that is the location of the point where the amount of shear is equal to 5 VC. So, based on the rules, we can say in this region, we don't need any stirrups. In this region, we need minimum stirrups. And in this region, we have to design the stirrups because the shear is greater than 5 VC. And I have to find the S, or a spacing between the stirrups. So let's follow the procedure to see what is the shear reinforcement that we need. Of course, the shear load, the maximum shear load that we need to consider in each part of the beam is calculated based on the code suggestion, which said consider D inches from the support. Over here, D inches from the support is the minimum value or the smaller values, but the important is over here where we have the maximum shear. So D inches from the support will be some shear at 21.5 inches from the support. And if I calculate that value, we can simply find the value based on the same rule of similar triangles. That value will be 36.27 kips. That is some value over here. I'm not showing it because it is just designing the stirrups for the whole region. I have to just consider the VS maximum shear, and that is located at D inches from the support. That's why I'm not showing it, to just show the regions that we have regarding the stirrup design consideration. So shear at D inches from the support was equal to 36.27 kips. Now that I have this value, I can use it in the equation that we had for finding the shear on stirrups. We said total shear of the section is equal to VC. Let me write over here. Total nominal strength is equal to VC plus VS, and that's how we can say phi VC plus VS, the reduced shear strength should be greater than VU. And if I put it equal to VU, I can find the amount of shear that goes into stirrups. So VC plus VS, let me clean. So VC plus VS will be VU divided by phi. And based on this, we said VS is equal to VU divided by phi minus VC. The equation that we talked about in the presentation files and we used for designing the stirrups in the example that we had earlier in the presentation. So based on this, VS, the amount of shear that goes to stirrups, is equal to 13.76 kips. Now based on this VS, I can find the spacing. This is the equation that we used for that. And as you remember, when we were talking about the cracks, inclined cracks in the web of the sections, we said those are 45 degrees approximately. Based on that assumption, we could come up with this equation, and now we are using this equation for finding the spacing between shear reinforcement. Using this equation, I am putting the value of Vs over here, and then based on this, I can see S will be equal to 13.75 inches. Of course, we had a limit. As you remember, we said whenever the amount of shear is greater than 5 VC, we have to design the stirrups based on this equation. That's what we did. But we have to make sure the spacing that we design is not greater than the maximum spacing limit from the code. And that is the minimum of these values. So I have to calculate that. Vs is smaller than 4 square root of f prime c. See, this is the limit. If it is Vs, if the Vs that we have is smaller than this value, we have to follow these limits. If it is greater than that, we have to follow these limits. In our problem, as you can see, Vs is just 13 kips, definitely smaller than 4 square root of f prime c, because we already calculated the 2 square root of f prime c bwd, and we could see that value was greater than this. So definitely smaller than that, and that's why the limit that we have for spacing is minimum of these values. These are the same values that we calculated before, and the result of these values or these terms was equal to 10 3/4 of an inch. The S that we could calculate based on this equation is greater than this, which is not good. So I have to take the maximum spacing limit and use that as my design for stirrups. It means that from this point to this point, I don't need any stirrups. And then from this point to this point, I have to provide the minimum stirrups, which means number 3 double leg bars at 10.75 or 10 3/4 of an inch as the spacing, right? So we could design the stirrups for this portion of the beam. We could design the stirrups for this portion of the beam. And now I'm going to focus on CD and design the stirrups for this portion of the beam. The procedure is exactly the same. I have to find the locations where the amount of shear is equal to 5 VC over 2 and 5 VC. And then based on that, I can say whenever shear is smaller than 5 VC over 2, we don't need any stirrups. And if it is between 5 VC over 2 and 5 VC, we need AV mean or minimum shear reinforcement. So at first, let's find the locations of the points where shear is equal to 5 VC over 2 and 5 VC. Over here, I can simply use the same rule, similar triangles. As you can see, this side over this side for this triangle is equal to the same ratios for the bigger triangle, which means 12.97, that is 5 VC over 2. Over this side, and we can say this is equal to total length, which I believe was 6 foot, which will be 86 inches, right? 6 foot, which will be 72 inches minus x is equal to the bigger triangle. The bigger triangle is this one. And for this one, I can say that ratio is equal to 28.8 divided by total length, which is 6 foot or 72 inches. Those ratios are shown over here. See? And based on this, I can find the location of having shear equal to 5 VC over 2 as 39.75 inches from point C. So that is the point where shear is equal to 5 VC over 2. And then the same idea for the location where the shear is equal to 5 VC. And if I use the ratios that we had between this triangle and the larger triangle, we can find the location of this point. And once you do that, you can see that is located at 7.12 inches from the support. So it means in this region, I don't need any stirrups. In this region, we need minimum stirrups. And in this small region, we are in the domain or in the range of d inches from the support. So I have to just extend whatever reinforcement I have before it into the support. So over here we need minimum reinforcement, which we calculated before. That was 10.7 or 10 and 3/4 of an inch. 3/4 of an inch as the spacing between stirrups. And over here, I don't need any stirrups. Those are mentioned over here. From point C to X is equal to 39.3 quarter of an inch. I have to use stirrups at 10 and 3/4 of an inch as the spacing, and then from that point beyond or to the end of the beam or point D, I don't need any stirrups. So if I follow these rules that I mentioned, this one, and then this one, and then this one, all the rules that we calculated for the stirrups in the beam, I can design the stirrups or shear reinforcement as you can see in this diagram over here. I said from point A to 62.75 or 62 and 3/4 of an inch, I have to use double leg stirrups at 10.3/4 of an inch. As you can see, these are the stirrups. Note that these blue annotations or these blue dimensions that I'm showing, these are the locations where we had 5VC and 5VC over 2. And as you can see, the stirrups that we are putting are based on measuring the spacing with tape measure. This is how they constructed. So I have to just make sure that I'm covering the regions that are important for me. And as you can see, these are covered by the stirrups. And in these regions, as you can see, these regions were the regions where the amount of shear was smaller than 5VC over 2. So there is no stirrups in these regions. And then from point B to point C, as you can see, there was a small region where we didn't need any stirrups. And then beyond that, we had to provide the stirrups at 10.75 or 10 and 3/4 of an inch as the spacing between stirrups. The location of stirrups are shown over here. And then from point C to point D, as you can see, in this region, we said we didn't need any stirrup, so there is no stirrups. And then in these regions, we needed minimum stirrups. That's why the spacing that I have between stirrups is the maximum, which was 10 and 3/4 of an inch. In this final diagram, I'm showing you the location of stirrups. This was a very important example regarding designing the shear reinforcement for beams. Please repeat this example at home, and if you have any question, just let me know and we can discuss it through email or WebEx meeting. Thank you.